Hello everyone, my name is Kian. Today I'll present the paper Causal Intersectionality and Fair Ranking. This is joint work with Josh Loftus at LSE and Julia Stoyanovich at NYU. Let us consider an idealized hiring process of a moving company that has a dataset of applicants, including their gender, race, weightlifting score X, and the overall qualification score Y, by which job candidates are ranked. The moving company wants to hire 4 best qualified candidates. The process by which Y is derived is hidden from us, but we observe each candidate's attributes, including their score. Consider the results and observe that only 1 female candidate and no black candidates are returned among the top 4. Observe also that weightlifting ability X maps to qualification score Y differently depending on gender. We may have reason to believe, based on our knowledge of discriminatory practices in hiring, that gender and race impact the qualification score Y. In this paper, we take an approach to fairness based on causal modeling. We assume that a suitable structural causal model is available that specifies relationships between variables, including the sensitive attributes, which define individual traits or social group memberships relevant for fairness. The causal model is a statement about how the world works and is represented in a directed cyclic graph, or DAG for short, where vertices represent variables and edges indicate causal relationships from source to target vertices. We assume that the causal model describes the data generation process, including what would happen under interventions or counterfactual scenarios. And our goal is to use this model to produce a ranking that is fair with respect to multiple sensitive attributes and the intersectional subgroups of these categories. We define intersectional fairness by modeling the causal relationships between sensitive attributes and other variables in the DAG on the basis of not just one attribute at a time, but a combination of attributes, and then make ranking fair by removing these effects. Given a ranking task and a set of sensitive attributes and a causal model, we propose ranking on counterfactual scores as a method to achieve intersectional fairness. We use the causal model to compute counterfactual scores Y tilde, the scores everyone would have under one specific combination of the sensitive attributes, gender and race in our example. We then rank the candidates based on these counterfactual scores to produce a ranking that would satisfy a causal and intersection definition of fairness. Let us return to our example. The arrows pointing from gender G and race R directly to Y encode the effect of direct discrimination, which are shown in red in the DAG. Additionally, the causal model can encode indirect discrimination. G and R both impact Y through weightlifting ability X, and X is called a mediator variable. How do we deal with the impact of gender and race on Y, both directly and through the pathway including X? Under U.S. labor law, the moving company may be able to make a business necessity argument for the weightlifting of variable X. The DAG on the left shows the case where X is a resolving mediator, meaning discrimination on the basis of X is considered unenforceable. The DAG on the right shows the non-resolving case, where no discrimination is allowed, direct or indirect. We want to check whether such causal links exist in our data, and if so, to break them to produce fair outcomes. Once the goal has been decided, we can then use the causal model to compute counterfactual scores, the scores that would have been assigned to the individuals if they belong to one particular subgroup, defined by fixed values of R and G, while holding the weightlifting scores X fixed in the resolving case, and then ranks candidates based on these scores. A mediator X may be considered resolving or not. This decision can be made separately for different sensitive attributes. And the relative strength of causal influences of sensitive attributes on both X and Y can vary, creating potential for explanatory nuance even in this simple example. This DAG shows a case of mixed resolving variable, where X is a resolving mediator with respect to gender, but not with respect to race. This means the impact of race on weightlifting ability X should be disallowed for ranking. On the other hand, the impact of gender on weightlifting ability X can be considered legitimate. This is an example of the expressiveness of our framework for intersectionality. We compare the counterfactually fair ranking for the movie company example with two other rankings, considering the selection rate for each intersectional group at the top K. The original ranking in the middle sorts on the overall qualification score Y. The ranking in the right is produced by quotas on race only. Specifically, we compute this ranking by independently sorting black and white applicants on Y and selecting the top individuals from each list in proportion to that group's representation in the input. Demographic parity is achieved if the proportion of the individuals belonging to a particular group corresponds to their proportion in the input, so the selection rate equals to 1. In these three plots, we show selection rates of 4 intersectional groups: white male in green bars, black male in orange, white female in purple, and black female in pink, for 3 kinds of rankings. The x-axis shows the size of top K set, and the y-axis shows the selection rate. Our results are over 100 executions. The left plot shows our results for the case where X is a resolving variable for gender but not for race. In the counterfactually fair ranking, selection rates are higher for the black of both genders than in the original ranking. The ranking from quotas on race on the right shows demographic parity for racial groups. Opting for quotas on race rather than on gender or on a combination of gender and race is reasonable here, and it implicitly encodes a normative judgment that is explicit in a causal model shown on the lower right, that race should not impact the outcome, while gender may, but only through X. Our framework also allows for numeric sensitive attributes, like age for example, where treating everyone according to one baseline counterfactual is possible, even though subgroup terminology breaks down. For example, we could produce a ranking of counterfactual scores based on everyone being a 45-year-old black woman. Additional details, including experimental results that showcase the flexibility of our proposed method, can be found in the paper. In this paper, we consider 2 types of ranking tasks: score-based and learn-to-rank. For score-based ranking tasks, we use the following procedure to compute counterfactual fair rankings. For an input dataset, we estimate the parameters of the assumed causal model. A variety of frequentist or Bayesian approaches for estimation can be used. From the estimated causal model, we compute counterfactual score on the input data by replacing the observed value of sensitive attribute, for example, white male, with the counterfactual, for example, black woman, and then propagating this change through the DAG. Any directed descendant of gender or race has its value changed, and this operation is iterated until it reaches all the terminal nodes that are descendants of any of the sensitive attributes. This yields a counterfactual fair data detailed with counterfactual scores. For score-based ranking, we sort Y tilde in descending order to produce counterfactual fair ranking. We then use it to assign outcomes. For learn-to-rank tasks, we then train a ranker on D tilde. We produce counterfactually fair ranking tau hat on test data using the ranker. We then use it to assign outcomes. When the distribution of scores Y differs across groups, then we may need to sacrifice score utility to produce a fair ranking. We evaluated the score utility of the counterfactual rankings using 2 measures: Y utility loss for score-based ranking and average precision for learn-to-rank. Both compare a ground truth ranking tau induced by the order of the observed score to a proposed fair ranking. We investigate whether the counterfactual ranking derived in our method is fair with respect to intersectional groups of interest under the given structural assumption of the underlying causal model. We consider two types of fairness measures, those that compares ranked outcomes across groups and those that compare ranked outcomes within a group. To quantify fairness across groups, we use two common measures of fairness in classification that also have a natural interpretation for rankings: demographic parity and equal opportunity for varying values of K. To quantify fairness within a group, we use a rank-aware measure called in-group fairness ratio, short for IGF ratio, to surface intersectional fairness concerns in ranking. Additional experimental results of IGF ratio can be found in the paper, and we also refer the audience to the archived version of this paper for experiments with other rank-aware fairness measures. We now investigate the usefulness of our method for learn-to-rank tasks. Assume we have a ranker that is trained on fair input data detailed following the introduced implementation steps. Now we have two options in the last step to produce the counterfactually fair ranking on test data. We choose an option considering whether the problem allows to use the causal model at test time. If it does, then we produce fair test data detailed by applying our method on test data as a pre-processing fairness intervention. If it does not allow the use of the causal model at test time, then we rank the unmodified test data. We refer to the two options as CF-LTR and LTR respectively, and emphasize that in the second case, counterfactual fairness may not hold or hold only approximately on test data. Note that the two options differ in whether to apply our method as a pre-processing fairness intervention on the test data. In both options, we train on counterfactually fair data. Details of experiment setting can be found in our paper. The plot shows equal opportunity on the moving company example with K equals to 200 over 50 training and test pairs. X-axis shows the two options CF-LTR and LTR with X as resolving or not. Y-axis shows the ratio of sensitivity between each counterfactually fair treatment and the original ranking. Intersectional groups are denoted by different colors. Solid boxes correspond to CF-LTR settings. A method achieves equal opportunity if sensitivity is equal across groups. The performance of the fair rankers, the CF-LTR variance in the left two columns, is comparable to the original ranking model in terms of sensitivity, with the medians of all boxes close to the sensitivity ratio of 1. The resolving variance, the resolving columns in the plot, show lower sensitivity for women, likely because women are selected at lower rates since X is treated as resolving for gender. The LTR variance, LTR columns in the plot, show lower sensitivity for women because the test set is unmodified in this setting. Finally, when the fairness intervention is applied on both training and test data, the CF-LTR columns in the plot, it leads to better sensitivity for women. Our work aims to mitigate the negative impacts of ranking tasks on people due to attributes that are out of their control. In this work, we proceed with an understanding that the model is a simplified and reductive approximation, and we support for transparent decision-making process to deploy an algorithm and claim its fairness goal by stating decision-makers' belief in the form of a causal model and not for rubber stamp. There are many issues outside the scope of the present work, but which are important in real applications, such as the choices of which attributes are sensitive, which mediators are resolving, and for which sensitive attributes. The social construction and definitions of sensitive attributes, choices of outcome, utility, or proxies thereof, technical limitations in causal modeling, and the potential for adverse misuse. All these issues may have adverse impacts when using our methods. We do stress that these are no limitations inherent to our approach in particular, Rather, these concerns arise for virtually any approach in a sensitive application. Further, like any approach based on causality, our method relies on strong assumptions that are untestable in general, though they may be falsified in specific cases. In summary, our work builds on a growing literature for causal fairness to introduce a modeling framework for intersectionality and apply it to ranking tasks. Experiments show that this approach can be flexibly applied to different scenarios, including ones with mediating variables, and the results compare reasonably to intuitive expectations we may have about intersectional fairness for those examples. The flexibility of our approach and its connection to causal methodology makes possible a great deal of future work, including exploring robustness of rankings to unmeasured confounding or uncertainty about the underlying causal model. Thank you. Any questions?